back now. Hopefully you had a chance to try some of these problems, hopefully all of these problems, and now we can talk about the solutions. So let's look at this first one, MUIU, and look at a derivation. We've got our 4 rules. What does the solution look like? Here it is. MI turns into MII. Can you see which rule that is? It's rule 4. Then we do it again. Another rule 4. We're allowed to add a U on the end if the string ends with just an I. That's rule number 1. So that's the next step. And then finally, we can replace the first 3 I's with a U, and there is our derivation. Okay, were you able to do that? I hope so. And one thing I suggest is for puzzles like this, an interesting thing that I found also, because I am not by nature a mathematician, I find that mathematicians have an easier time, maybe because it's just less stressful, it's normal, their normal work mode, they just try things. Right? They have intuitions about what might work, but they're not too hung up on just trying stuff, trying some transformations to see if it gets them closer to that answer. So when I'm coaching people on this particular problem, as well as other problems in logic that are more difficult, I suggest as a start, in order to develop practice and develop intuitions about what works, you've got a bag full of rules. Try them. Try random things, and you'll learn over time. Your mind will find patterns that helps you find the answers. And on problems that are as small as these, that's really powerful, and it prevents you from getting stuck. So if you find yourself staring at the page, trying to figure out what to do next, stop. Don't worry about that. Just start applying rules. Apply them randomly. Apply them mechanically. And you'll get to your answer probably much faster. When I do this in a classroom environment and I see people just sitting there, I say, wait, just try stuff. Be a machine, and then you'll figure it out. It really works well. Okay, next one. This one's a little bit longer derivation. We turn 1i into 2, into 4, into 8. Then we add a u on the end, applying rule 1. Then we look at the last 3 i's and we turn them into a u. And finally, we can remove the last 2 u's using rule 3. Right? So see how we got in problem 2, we were looking for 5 i's. We start with just 1 i, and then we have to do some doubling and then some removals to get down to 5 i's. Right. Now let's take the third problem. It's again a little bit harder. Each one is a little bit harder than the previous one. So we do something very similar. We get up to 5 i's. Actually, sorry, here it looks like we're missing a step, but it's a step we've covered previously. So we go from 1 i to 2 i's to 4 i's, then to 8. Then we replace the first 3 i's with a u. Replace the first 3 remaining i's with a u. We then double that string using rule 4. Then let's see, what do we do here? I think we're removing the doubled u. All right, that's rule 3. And then finally we are taking 3 i's and turning it into a u again. That's rule number 2, right? And that gets us to MUUUI. That was our original objective for problem number 3. Now, the last one, as I mentioned, is a trick question. If you played around with it, you find it's just, you just can't seem to get any closer to that target string of MU. You've always got pairs of U's or more. Okay. So MU cannot be derived. Here's an attempt to give a proof, a sketch of a proof. So we always start with MI, and we call that the invariant. It doesn't vary. And the number of i's that we have, we can bring back our use of this cardinality operator, the vertical bars. So at the start, we don't have three eyes. All right. Okay. Let's see. Then here's just the next sub-bullet stating formally, so mi, this particular instance, is not divisible by 3. Rules 1 and 3 don't change the number of eyes. They're actually not relevant for our problem, because we're really trying to get down to not having any eyes at all is the key thing. We're sort of focusing on the eyes and ignoring the u's in our derivation at the moment. Rule 4 doubles the number of eyes. Okay, so we can have 1, 2, 4, etc. And Rule 2 reduces the number of eyes by 3. But in no case does a non-multiple of 3 become a multiple of 3. So play with that a little bit, see if you can convince yourself of that fact. But we have to have the cardinality of I being 0. Okay, and so as a result, it's not possible to get rid of all of the eyes. Okay, because the only way we can get rid of eyes is by applying Rule 2. In the end, we'd have to have a step that turns MIII into MU. That's the only way we can get to the answer we want. And so we're able to sort of go backwards in our proposed proof one step and create a line of reasoning that just dealt with one small portion of the system, just the I's instead of the U. Because we have to get to that step in order to get to the final step. We have to get to MIII in order to get to MIU, because that's the only way we can reduce the size of the string down to just one character following the M. Right, so the next step on this problem is to actually write code that will do this computation, but do it mechanically, like I was recommending that you try, instead of just relying on intuitions about what might work, intuitions that you don't have because you haven't had a chance to practice with the system very much. So you can write this in Python. Most people are writing code in Python these days. I myself am a Java programmer, so if you want to write it in Java, I'm fine with that too, or any other language, because unless I'm working with you already, I won't have a chance to critique your problem. You're going to have to find out whether your software works just from whether it comes up with the derivations that we've done as examples. Those are going to be your test sets. In order to get started, to break this down, if you're not, or if you're already a professional programmer, just start writing it, no problem. If you're not a professional programmer, if you haven't been coding for several years, or if you haven't been coding intensively in a computer science degree program already for a couple of years, you might want to approach this a bit more step by step. So here are some ideas to help you approach the problem and not be stuck. Start by writing just some Python functions or Java functions or what have you that implement each of these 4 transformation rules. So they should take in a string and output some kind of collection of strings, right? Because remember that rules 2 and rule 3 have the possibility of applying to multiple positions inside a given string. So although the first and the fourth rule can only transform one string into one other string, rules 2 and 3, if you have really long strings, can transform one string into many possible strings, right? So remember, if we had M and 4 I's, rule 2 could give us MUI as well as MIU. So 2 possible outputs. The same is true for rule 3. So if you're in Python, you could use lists. You could also use a list of structures. There are lots of different ways to do this. In Java, you could use an array list. You could use a hash set so that you already are avoiding duplicates in your output. But in all cases, you'd be manipulating strings, whether in Python or in Java. Right, so each function that you write should take in a string and output a set of strings so that you have a uniform interface for each of these 4 operations, even though the first and the last rule will only generate a list or a set or a collection of just one string. I'd encourage you then to write some test functions for each rule. You can use JUnit or Python's unit testing framework is what I would recommend. I'll have a pointer to those things in a moment. And have a test for each rule that takes some hard-coded string that you put in the software and then has a target for what the result should be. You know when you write a string and apply one of these rules to it, you know what the result should be. So put that in your code. Have a string of the input, which is always which could be mi, because it's just a test, but it could be a more complicated string, and then write what the desired expected output or outputs should be from each of these rules, and have your little test routine report whether the test was passed or not. Did the routine in fact generate all the outputs that you expect? Then write a parent routine that tests all of them just for convenience. So you can essentially have a one command test for your whole system. Okay, for step 4, we're going to need a routine that tries each rule and generates a set of results. Remember, every derivation starts with mi, and we'll have a target that we want to get to, and we're going to keep generating possibilities. We're essentially elaborating a tree. We're starting with only one possibility, and if we start with mi, for example, we have 2 things that could be generated. Right? We could apply rule 1 and generate miu, and we could apply rule 4 and generate mii. After we do a round of applying rules 1 through 4 to our input, we're going to have a set of outputs, a larger set of outputs than the inputs that we started with. And then we're going to go through another iteration of trying each of the rules on our set of inputs, because we won't have just one input, we'll now have a collection of inputs. We'll need to apply rules 1 through 4 of our new set of miu and mii. That in turn will generate, I think, 4 different possibilities. So we'll cycle again. You might think of these as epochs or layers of the graph, layers of levels of the tree might be a better way to say it. So you're going to need a routine that constantly iterates through the set of things the system is working on. It's going to start with one thing, then it's going to have 2 things, then it's going to have 4 things, and it might have then varying numbers of expansion, but it's always going to be getting bigger. So this is one of those systems that the search space is constantly expanding. And so for these more complicated strings, longer strings, the derivations are also going to be longer, and they're going to take more time to find. Lastly, now that you've got your function for each of the 4 rules, you've got a kind of supervisory function that iterates through all of the possibilities in the system, applying all the rules and generating a new level, a new set of strings to apply the rules to. You'll also need a function in that loop that checks to see if you've come to the answer. So you should have a top-level routine that starts with mi and keeps generating levels and levels below until the answer is found, at which point it can terminate. So here are some questions to ask yourself as you go through this exercise. What results do you get? You shouldn't get a result for the last problem. If you do get a result for the last problem, you've got a bug in your system. And you should maybe have a counter in your system. It's something you can add that would report back to you how many steps did each of these solutions take. You might also set a timer to see how much time each of these solutions took. So here we are. This is our first exercise for the course. I hope you enjoy it, and I hope I've given you enough information such that you can verify your own code. And then we'll talk about some possible refinements on this as well. Let's talk a little bit about test-driven development. This is something maybe you can consider before you start writing your implementation of the MIU problem. The idea of test-driven development, I think, is very powerful. It says, think of the endpoint first. What are the results that you want your code to achieve? And this might be small individual results, or it could be larger results that are the combinations of many operations. And if we know what those results are, then we can put them in place first before we write our code, so we have a formal specification of the endpoint that we want to reach, code that produces a certain set of answers for a certain set of inputs. And if you're disciplined about this, you'll write very good code. And also if you make use of the features that are available in Python and Java and other languages, then you'll also have a regression test suite. You'll have something that is a collection of tests that whenever you modify your program, you can run this series of tests and get a report back. Did any tests fail? Now that could be because you've decided to change your requirement specification, that you want your program to perform differently, or it could mean that you've introduced a bug, you've broken something, and adding new functionality, you've made some old functionality stop working. And this is the bane of most programmers' existence. You're always trying to make your code better. Maybe your boss has changed your requirements, or your customers changed your requirements, and in your haste to satisfy those new requirements, you wind up breaking something. And if you don't have a regression test suite, if you don't have a unit test suite, it can be often hard to even know that you've broken something. But if you have a good collection of good coverage of the performance of your system, then you can press a button, get a report, and know, hey, I just changed something, I broke something else, and it's going to be fresh in your mind when it's easy to go fix it. As opposed to if you don't have a testing system like this, you could be in a case where you break something, a couple of months goes by before anybody notices you broke some old functionality, and then you're going to be racking your brain about, well, what did I change? I've changed so many things over such a long period of time. How can I go back to that one point where I broke something and fix it? It's so much easier if you know right away, at the end of every day, maybe you run your regression test suite, and then it'll be easy to remember what you did that day and go back, hopefully, and fix what you broke. So I really recommend this approach. Here's just an example in Python. Let's say we have a class called calc that has an initializer where you're just supplying two values to the member variables of the system, and one routine that returns the result of adding those two values. So utterly trivial, just so that we can see the simplest, minimal working example of using unit tests. So if you create then the following, a class that tests the first class that you've created, you create the values in the system. So this first line under the def test sum says, all right, create a version of this class that has the values 8 and 2, and assert whether they're equal. And just for now, I've included the wrong result, so that if you run this, you can see the system report back that an error has been found. So here it's saying, 8 and 2 equals 6, and obviously that's wrong. So the self-assert equal will report back saying the sum is wrong. Right? So of course you can fix that. Also see how it performs when you give it the value of 10, the correct answer. Okay. So here's what you should get. So 10 is not equal to 6, obviously. The sum is wrong. Gives you a report of how long it took. It says it ran one test and it resulted in one failure. So if you have lots of tests, this really helps because it'll give you a report of how many tests fail, which they were, and how much time it took. So just a really helpful method for software development. And conversely, if you change the value to 10 instead of 6, then you get that it passed all tests, all one test that we have giving the correct result, and it tells you everything's okay. So after you've developed the first version of this program, here's a more complete assignment if you choose to accept it. Executing the program should result in a display of at least one test input and the results for each rule. So execute all your Python unit tests. Right? Each rule should have a unit test that goes along with it. So there should be at least one input for each of those 4 rules, and it should have an expected output that you can see as a result of using the unit test framework. And then also have a routine that tests each of the 4 test problems, including MU. And the result of each of those test problems should be displaying the input and a derivation of the result. And again, if you're already a professional programmer, an accomplished programmer, you may be able to just come up with an approach for capturing the derivations. So derivations we've been over previously, so it shows each step in going from MI to the result that your program has been asked to achieve, one of these 4 results. And it should present essentially a proof of derivation that says what is the rule that was applied in going from one string to another, and show them all in order from start to finish. And that's what this example here does. So you start with MI, it doubles the end, it doubles it again, reduces the first 3 i's to a u, applying rule 2, and then finally applies rule 4 to double again. That was our first test problem. So this is a good example that you can put in your unit test framework. Or really, you might call it an integration test, because it's testing the system end to end. It says, here's an input for the entire program that you've written, and here's what it should give as an output, a derivation in this following form. Keep in mind, you just want to report the path from start to finish, and not all the other things the system has tried, right? So we could have applied a different rule in the first step. Instead of going to MII, we could have a U at the end as one of the rules. So we could have MIU. Well, that doesn't get us to the answer. At least it doesn't get us this particular derivation to the answer. So just show the step that actually mattered, that got you to the answer at every stage, and report which rule was used in that transformation. It's also the case that the program should terminate gracefully if no result is found. Just basic good programming practice. Don't have your program hang. Right? If you get an input that can't lead to a solution, like MU, that's the one that is impossible in our formal system, we've proved it. Don't have the program just hang, have it do something to terminate gracefully. Have it keep a counter and say, well, after 1,000 applications of different rules, if I haven't found the answer, then just give up. And see what value for that counter works for you. If you design the counter well, then you should get a termination that's graceful in a reasonable amount of time. If you designed it poorly, well, it still might take too long and you'd be very tempted to hit Control-C. So try to play with that a little bit. And if you're not an experienced programmer, I'll do another video that gives you some hints on how you might create this data structure that will record derivations and how you might use that in this program. All right, that concludes my first lecture. I hope you found this a helpful introduction. I hope that exploring this very simple logical derivation system, this simple logical framework, will give you an insight later on for what might be happening behind the formal systems that we introduced that are far more complex and more powerful. So thanks for watching, and I'll see you in the next video.